Welcome to today's Dev Engineering Hours, and today we are going to look at STM32 reset and control, the clock control and also the timers. And we're going to look at the STM32 block diagram, see where we can locate this peripheral, also the clock system view, understand different sources of clocks that can be used to run the system clock. You can also look at the importance of clock and timers, the types of timers and their features, timers and interrupt, and see how we can use this tool to generate a timer update event, and also PWM signal generation using the timers, and we should discuss how you can do your calculation to achieve your desired duty cycle, how you can also achieve fixed and variable duty cycle, and finally we shall highlight a few things about the applications of the PWM signals. So this is the block diagram of the board that I'm using. Just use another one here. This is specific to STM32F446RE. So you might want to check the datasheet of your microcontroller if you're using another series. Has a different block diagram. Of our interest today is the reset and clock control. And what this peripheral does is managing the system clocks and handling the reset signals. So just to mention, we have a few ways that we can generate reset signals, and one is power on reset, which occurs when the microcontroller is initially powered on. We have external reset, whereby you can ground the NRST pin provided by our STM32 chip. We also have the brown out reset, which is activated when the power supply drops below a certain threshold. And we have other things like the independent watchdog and the window watchdog timers, and also software reset. All these is controlled by the reset and clock control. So for the clock control, the RCC manages the clock signals for various parts of the microcontroller. We have the HSE, or the high-speed external. You can see that we have the HS here, high speed. The high speed can be internal or external. So we shall look at that when we are looking at the clock configuration. And we also have the LS, the low speed. So we have also the low speed internal and the low speed external. So for the HSC oscillator that is used to generate high speed signals, this is a crystal that is used for high precision clocking. And for the high speed internal, it is embedded to the microcontroller and provide lower precision. So if you really need high accuracy timings and such, you might really want to choose an external oscillator. So inside the reset and clock control, we have the phase locked loop, which are used to generate high frequency signals from the HSE or the HSI. So sometimes you may have a smaller signal frequency that's around 8 to 25 megahertz, and you want to generate an 80 or 120 megahertz. This is where the phase locked loops come in. So we have the system clock, which is the main clock signal that is used to by the CPU and the peripherals. And the peripheral clocks, these are provided to the individual peripherals like the UART or the SPI. So the key functions of the reset and control clock, one thing is selecting the clock source and the frequency of the system clock and also the peripheral clock. Another thing is the reset management, which configures the behaviors and response to different reset events. And finally, it provides the clock security system, which monitors the integrity of the main clock. Um, Usually the HSE or the high-speed external, and switches to the safe mode or the state if it fails. So alongside here you can see that we have the power management part, and this part plays a critical role in managing power consumption and optimize energy efficiency. That is why we have things like the sleep mode, the standby mode, and the stop mode, just to ensure that we have low power consumption. So the key functions, another key function of the power management is voltage scaling, because you find that the STM32 supports multiple voltage scaling levels. You can see from here it's 1.8 to 3.6 to 3.6 for the STM32F446, and you can change this just by software configuration. So the power peripherals allow software control over these voltage levels, enabling dynamic adjustment based on the performance needs to balance power consumption and process requirements. So we also have other things like the VBAT. You can see that we have some powered by the VDDA and some powered by the VBAT. We have the external 32 kilohertz LSE on the low speed external, which is used to run the RTC and the backup RAM and also the backup registers. So you find that these, even when the reset occurs and you have connected your VBAT to the board, these registers are not reset. So they keep the updated values. So another thing to mention is about the timers. You can see that we have timer 2, timer 3s, which are connected to APB1, which runs at maximum frequency of 45 megahertz. And we have other timers like timer 9, 10, and 11 connected to APB2, which runs again at a maximum frequency of 90 megahertz. So yeah, that's it. So let's go to our presentation and look at the clock system overview, how we can select different clock sources to run our system clock. So I'm going to start the STM32 Cube MX. Let me create a new project here. So I'm going to select the board that I'm using, Nucleo F446RE. The project, and first thing that I'm going to do is clear all the pinouts. And if we come to the clock configuration settings, you'll find that we have the clock tree provided for us. This will help us choose the clock source for our system clock. And from the top here we have the low speed external, which runs at 2.768 kilohertz, and this is used to drive the RTC. So just to mention, this is a very accurate crystal. You may find that when you use the low speed internal, the accuracy is a bit off because it is affected by things like temperature and the voltage. So we also have the LSI running the independent watchdog. So the independent watchdog is used just to provide reset when the refresh does not occur between the set period. So we have again the HSI, the high speed internal, which is 16 megahertz, and this can be used as a source of clock for a system clock. and it can also go through the PLL source mix so that we can generate high frequencies from the 16 megahertz. So you can see from 16 megahertz we can achieve even to 180 megahertz, and you find that we have things like the APB1 prescaler and the APB2, and from the block diagram we saw that the maximum frequency of APB1 is 45 and our maximum clock frequency for the APB2 is 90 megahertz. So you can see that the frequency runs the clocks and also timers, the peripheral clock and timers for each of these two, the APB and APB1 and APB2. So we also have the high-speed external. This is a crystal oscillator that is it's designed with the board or development board that you have. So in my case, it's usually an 8 megahertz crystal that I can select by just coming here at System Core under RCC. I can select the high-speed external, and you see that it will be available for us to choose, and you can also use these to provide the system clock frequency. And also we have the PLLs that ensures that we get high frequency also from the high-speed external. So another thing to point out is the master clock output. So for this one, they're usually connected to the pins, so that you can maybe measure the frequency by using an oscilloscope, or you can use one MCU to provide the clock to another MCU instead of having two crystals at the same time. So how you select this, just need again to come to the RCC, then you can select the master clock output one, and you can see that this is pin PA8. If you connect an oscilloscope in this pin, then you'll be able to measure the frequency, and you can use this pin to provide the clock to another microcontroller. And you can see that we have two, so yeah, you can choose whatever you want. So another thing to mention is that you can see that every peripheral has some frequency to run with, and you can set this by just choosing your desired frequency. So it's also good to point out that before you configure peripherals, the clocks are not usually enabled so that you can save the power. But if you really need to use a peripheral, then you must ensure that you enable the clock to that peripheral. So assuming you want to use a GPIO pin, you must first enable the clock to that pin even before you use it. So let's look at the importance of clock and timers. So the first one is this synchronization and timing control. So the clocks provide synchronization, whereas timers provide precise control over timing intervals and periodic events, and also create delays within the system. So whenever you say that hard delay this time, then you use the timers. So we also have the power management, like I mentioned. That's when we have the sleep mode, the stop mode, and the standby mode that are also managed by the reset and clock control. We also have the system monitoring and diagnostics. Those are used by the independent watchdog timers and also the window watchdog timers to check the health of the system. So if your code runs maybe at 1 milliseconds or 1 millisecond, and the refresh happens beyond 1 millisecond, then means that the system has password modulation. So the password modulation are used to control, these are signals generated by timers. For the password modulation, you can generate password signals that can be used to control the motor speed and also the brightness of the LED, and can also be used in voltage regulators. So peripherals and interface synchronization. I find that the clock synchronizes all the peripherals just to ensure that we get all the data transfer synchronized. So you have different types of timers in our STM32 F446. We have basic timers, general purpose timers, and advanced timers. And for the basic timers, you can see that the counter resolution is 16-bit. We also have general purpose timers having 16-bit, but we have timer 2 and timer 5 having the highest counter resolution, which is at 2-bit. And the counter type can be up or down or up down depending on your project. So we also have the prescaler factor that is used to scale down the frequency, and you can see that you can use any value between 1 and 655, that's 6. And you can also see which of these timers supports DMA request generation. We have capture compare mode channels, like the timer 2 and timer 5 have 4 compare of capture compare modes. That means you can even generate a 4 PWM signal using one timer. We have the complementary output advanced control timers like timer 1 and timer 8 have this feature, and you can also check the frequencies that this timer runs on. So timer setting in STM32 by D. So basically how the timer works is that gets the frequency from the peripheral clock, and then use a prescaler to scale down the frequency, and then this frequency at this frequency is the one used to increment the counter value. So you'll find that in every timer you set the auto reload register or the maximum value that you want to count, and then when this count elapses, then an event can be generated, or you can be notified that the count has elapsed, and maybe you can take action. So maybe you can do one project on that. So I'm going to submit work, and yep. So let me just reset all this, and I'm going to use pin PA5 as output. Give the pin a name LED, and I'm going to set the RCC. I want to use the crystal oscillator external. I want my system clock to be at 16 megahertz. Yeah, let me just use 16 megahertz and just ensure that the APB1 runs at 16 megahertz also, and this one too. So you can see that we have 16 megahertz to our APB1 peripheral and APB1 timer clocks. So I'm interested on the APB1 timer clocks because it's the one that is used to run the timer 2 that we are going to use in this project. So go to timers and select timer 2 and select the clock source to be internal, and under NVIC setting, this is the nested vector interrupt controller. I'm going to enable the timer 2 global interrupt, and in the parameter settings we're going to provide a prescaler of 10,000. So that means we have divided 16 megahertz or 16 million by 10,000 to get 1600. And then I'm going to count now to that 1600. So this will take 1 second to count from 0 to 1600. And what I want to do is to have an update event. to tell us that the time has elapsed. And yeah, let's go to our project manager, give it a name. So let's go ahead, update event. I'm going to give my project a name, which is this, and select our toolchain or IDE. So I'm using Kelly Vision. Let's generate the code. And our project, for main.c, I'm going to select the version and then view the code. And under user code begin to, we're going to start our clock. So timer base start with IT with interrupt, that is, and it's timer 2. Okay, and we're going to start our timer, and then when the count value of 1599 is reached, we shall have a callback that will notify us that the count has elapsed, and we can find these in the STM32 f4 underscore high time.c. So let's go to HAL timer period elapsed callback. So I'm going to copy this, put it in my user code begin for. So whenever that value is reached, so this will be called, and we can just toggle the LED here. So GPIO toggle pin. So it's green LED port, green LED pin, and probably we want to see the value of the auto reload register, or maybe the count. Let's see. So we can declare a variable here. Int32 CNT value is to 0. So is equals to STM instance, and then we want to get the CNT value, the count value, and let's plug our code and run this. So I'm going to add the count value to our watch one. Maybe you want to view the decimal values. So if you can see from the video that our LED is blinking, and we can add a breaking point at this point, and you see that the current value is 0. Let's see, let's read. It's 0, that means it has been reset. For the PWM signal generation, we're going to now blink the LED using the PWM signals, and the timer update frequency is similar to what we did in the previous section, where you take the timer frequency, then the auto reload value plus 1 multiplied by the prescaler plus 1. So what happens is that we have the auto reload value here at maximum, and then we have the counter register incrementing from 0 to the auto reload value. Then when this matches what is in the capture compare register, then a signal is generated. So let's see how we can achieve the blinking of the LED using the PWM generation. So I'm going to create a new project. I'm using F446 RA, start project. Then clear the pinouts. I'm going to select pin PA5. Again, you can see that we have timer 2 channel 1 for the PWM generation. Then I'll go to timers, timer 2, and I'll have the clock source to be internal clock, and I'm going to enable timer 2 channel 1 to be PWM generation. You can see that it has been enabled. Still, since I want to run everything using 16 megahertz, I'm going to use the same values. 15.9. And the pass I want to achieve 50% duty cycle, so it will be 1600 divided by 2, which will be 8000 minus 1. I mean 800 minus 1. So this is the same as 1600 minus 1. And let's go to our NVIC setting. Enable the global interrupt for the timer 2. And finally we come, you can go to the RCC, enable the external or select as our clock source, and also select these and make sure that everything is running at 16 megahertz. So let's give a project a name. So the heads underscore PWM. I'm using Kelly Vision. So let's generate the code. Open the project. So I'm going to select the compiler. With the code. I'm going to start my PWM. So have timer PWM start with IT, and I'm using timer 2, and then timer 2 channel 1. So let's build that and let's load the code to our board. I'm going to reset, and you can see that we have a PWM signal 50% duty cycle, so the T on is equals to T off, and this happens after every 1 second. So you might want to get notified after the pass has elapsed. You can find that in the functions. Let's go to our timer.h or .c, and you'll find HAL time PWM pulse finished. So we can be notified that the pulse has finished being generated. So you can come here, and every time you have the pulse completed, then you can increment a value. So I'm going to declare a variable that we shall increment. So let's have new int that's t counter. So we want to count how many times the pulse has finished. Let's count user code begin from, and we want to perform an increment. So let's build these, and session. I want to add this counter to watch 1. And let's see. So you can see that every time the pulse has elapsed, we increment the value of counter. So just to show you that it's been incremented in this callback, if I add a breaking point, you'll see that the code will stop at this point, and I can continue. So you can also, this is the fixed duty cycle. You can also achieve variable duty cycle by changing the value in the CCR1 register, and this is what is in the system configure.parse. So if you look at the CCR1 register, it will have the value of 789. So maybe I can show this, and I'm going to add timer 2 to watch 1. And if I go to timer 2 instance and CCR1, here we are. So I'm going to run this code, and I'll need to change this to this. You'll see that we have our CCR1 register value is 799. So if you want to achieve a different duty cycle, you have to change the value in the CCR1 register. So to achieve this, let's have an example here. I'm going to have 32_t and CCR1 update. You can call it update value. Starts from 0, and I want to increment it by 100 in the while loop, and I want to ensure that we can have the value changed. So timer 2 dot instance, then we have the CCR1 will be equal to CCR1 update value. Then we want to increment, we want to provide a delay so that we can be able to see from the LED, so after every 5 seconds. So, and we just want to make sure that the value does not exceed the auto reload value, so we can just do a simple if CCR1 update value is greater than the H timer HTM32 dot instance of the auto reload value, then you can reset this value to 0. Okay. So what I'm doing, just want to make sure that the update value does not go beyond this value of, let me show you the auto reload value. It does not go beyond 1600 or 15999. Okay, so good. So let's build. Let's go to debug session, and let's just add this to the watch 1 also. And what else? Yeah, probably we can also have the, now we can just see the CCR1 from this point. So let's start our code. You can see that our CCR1 value is 100. Just look at how the LED is blinking, and this will change depending on the current value of the CCR1. So we are changing the duty cycle from 0 to 1. Seems that it's not changing, so let me just invert this somehow. Let's have a delay here instead, just after. So yeah, let's see. Yeah, you can see now changing. So until we get to 1. So that's how you can achieve the variable digital cycle. So the application of the PWM signal ranges from its application in the motor control. So we can use this to control the speed of the motors. We can also achieve the LED dimming. We can these signals are used in inverter designs. We can also control the servo motor and also used in voltage regulators like the buck and the boost converters, and so many other important applications. So thank you guys for being with me. If you have any question, feel free to drop it in the Discord channel, and thank you for being a dev head.